Okay, in this flipped lesson, we are going to start to look at redox reactions, and we're going to look at the concepts of oxidation and reduction. Let's get into it. Okay, I've got a link up here to a good crash course video on redox reactions that might be worth having a look at just as a bit of an intro as well. Most of that will also be covered in these flip lessons, but it just gives you another good overview of this sort of stuff from a different source. So firstly, redox reactions probably I would say are better described as electron transfer reactions. They are all about things losing or gaining electrons. And in some ways we can compare them to proton, which is basically a hydrogen ion. If you take a hydrogen atom and take away its electron, all you've got left is a proton. They're very similar to proton transfer reactions, which was the whole basis for the acid-base chemistry that we did earlier in the year. Acids can donate or give away a proton, bases can accept a proton. Whenever you've got an acid reacting, you also need to have a base, so something gives away a proton, something else accepts the proton. So there's a lot of similarities in what we look at in terms of electron transfer reactions. The electron transfer reactions are probably a little bit more common and in some ways get a little bit complex. Now, we've already talked about some electron transfer reactions without really calling them out for being electron transfer reactions, for lack of a better term. So when we looked at corrosion reactions, if we look at something like magnesium metal reacting with oxygen gas to form magnesium oxide. To balance this out, we'd need a 2 there and a 2 there. If we look at the magnesium here, basically each magnesium atom would have the same number of electrons and protons. So magnesium is element number 12. So the magnesiums here would have 12 electrons. However, when it forms magnesium oxide, it donates those 2 electrons in the outer shell to become a 2+ ion, so it has only 10 electrons. So it's effectively lost 2 electrons. So we have had the transfer of electrons. Oxygen does a similar thing. I'm not going to talk about it at this point. I'll talk about that in the next example. So in this example, we have the combustion of methane in the presence of oxygen. It's complete combustion, so we get carbon dioxide and water. So this is the sort of combustion reaction we looked at in the organic chemistry topic. Now, what you can see here is oxygen, element number 8. Each oxygen atom in O2 has 8 electrons. However, when the oxygen forms water, it basically, because of its greater electronegativity, it sort of takes those 2 electrons into its shell from hydrogen. So effectively, each oxygen atom now has 10 electrons, giving it that full outer shell. So there's 2 in the first, 8 electrons in the outer shell. So the oxygen's effectively taken 2 electrons in this reaction, and it's taken those from basically the hydrogen. We won't worry about the detail of that yet, we'll come back to that later. But once again, it's an electron transfer reaction. Electrons have been transferred. Let's get into some more detail. So to start off really getting into this topic, we need to understand the concept of oxidation number. And the oxidation number is the number of electrons that an atom either gains or loses in order to form a chemical bond with another atom. So if we think about what we just saw on the last slide, we had magnesium losing 2 electrons, magnesium metal losing 2 electrons when it formed a bond to form magnesium oxide. We saw oxygen gaining 2 electrons when it went from oxygen gas to being in water in the combustion example as well. So we had this idea of loss or gain of electrons and that number. So oxidation is the loss of electrons, and I'll come back to the second part of that sentence in a second. And reduction is the gain in electrons. So essentially, when something loses electrons, when something donates or gives away, loses electrons, we have a positive oxidation number. And when something gains electrons, in the same way as when something gains electrons, it becomes negatively charged, we use a negative oxidation number. So there's quite a strong link between the oxidation number and charge. They're not exactly the same thing, but they are very similar. So firstly, when we want to work out the oxidation number of a pure element, the oxidation number of a pure element is 0. So if we have a metal like pure magnesium or pure oxygen gas, or even an inert gas, we don't really deal with those very often, something like neon. In all of those cases, the oxidation number will be 0, because obviously if they're not forming any bonds, they're not gaining or losing any electrons. Or in this case here, it's, if you like, it's a completely non-polar bond. Both oxygen atoms share the electrons equally, so they both effectively have their own 8 electrons. So they're not giving away or taking any other electrons. So any pure element, oxidation number is 0. If you have a monatomic ion, and by a monatomic ion, I mean something like a, sodium ion, or a chloride ion, or a calcium ion, or a sulfide ion, then the oxidation number is equal to the charge. Now note, we usually write for oxidation number the sign first and then the number, whereas with charge we tend to do it the other way. So chlorine is -1. So calcium isn't an oxidation number of 2+, that's its charge. Its oxidation number is +2 as opposed to 2+. Sulphur is not 2-, it's -2. So that's the oxidation number of a monatomic ion. Now the sum of the oxidation numbers in a molecule or polyatomic ion is equal to the charge. So if we have, say, water, a molecule, or a polyatomic ion, like, say, the nitrate ion, which has a negative charge, the sum, I'll put that bracket in to indicate, the sum of the oxidation numbers there would be 0. The sum of the oxidation numbers there would be -1. We'll come back to why that's important when we do some examples at the end. Now, the oxidation number of hydrogen is usually +1. So if we have compounds like our methane that we talked about before, or if we have H2O in water, the oxidation number of the hydrogen is +1, +1. However, obviously, I don't even need to write that down. If it's in pure hydrogen gas, we go back to that first rule. So it's a pure element. So in pure hydrogen gas, it would be 0. I will write that down. But remember, if you saw pure hydrogen gas, you sort of do these rules in order. So that would be 0. Now, oxygen is a little more confusing. The oxidation number of oxygen is usually -2. So in things like water or carbon dioxide, the oxidation number of the oxygen will be -2. However, if we have hydrogen peroxide, in hydrogen peroxide you can sort of see there, overall that must be 0 if the hydrogen's +1. That's not going to work if oxygen's -2, and it doesn't. In that case there, the oxygen is -1. So in a peroxide, the oxygen is -1. And obviously, if it's pure oxygen, like I've just said at the top and about hydrogen, then the oxidation number in a pure element is 0. So, there, if you like, our rules for working out oxidation number. Let's see some of those in action. So let's say we wanted to know what is the oxidation state of manganese in the permanganate ion. This is called the permanganate ion. What is the oxidation state of manganese? That would be, I'll show you how we work it out. So I do like this like a little algebra problem. So what we're trying to work out is manganese, so I just leave that symbol, plus 4 oxygen, so that's 4 times -2, and that's equal to the overall charge, which is -1. So Mn -8 equals -1. To get rid of the -8, we add 8 to both sides. Hopefully you're good at algebra by this point. So we get manganese is equal to -1 plus 8, which is equal to +7. So the oxidation state of manganese in the permanganate ion, MnO4-, would be +7. If we looked at what is the oxidation state of sulphur in sulfuric acid, H2SO4 here in the middle, we would go, well, hydrogen is 1, so it's 2 times +1 plus whatever sulphur is, plus 4 times -2, and overall that's equal to 0 because there's no charge on this one. So we get 2 plus S minus 8 equals 0. So 2 and a -8, it's going to basically give you S minus 6 equals 0, so it's -8 plus the 2. And then we add 6 to both sides to do the algebra. So the oxidation state of sulphur is equal to +6 in sulfuric acid. And finally, we'll look at the aluminium oxide. What's the oxidation state of aluminium? You can probably guess that aluminium is going to form aluminium oxide is ionic, so you've got the aluminium ion and the oxygen ions. Oxygen is 2-, aluminium is 3+. But let's just say you wanted to work it out for the theoretical activity of it. We would say 2 times the aluminium plus 3 times -2, so it is sort of going to turn into a minus in a sec, is equal to 0 because there's no charge. So 2 times aluminium minus 6 equals 0. My dog is barking, sorry. Aluminium, we're going to add 6 to both sides to cancel that out. So we get 2 aluminium equals 6. We divide by 2 on both sides to get rid of the 2. So aluminium will be equal to 6 divided 2, which is equal to 3. I hope you could hear that all okay above my dog barking. Okay, so now we need to learn how to write redox reactions and write equations for redox reactions. And we're going to do that using a strategy called the half equation method. And in particular, we're only going to be looking at what we would do under acidic conditions. That's all we need to worry about in both this year and next. Makes it a little bit, it gets a bit more complex if you don't have acidic conditions. There's going to be some similarities here with when we did acid-base reactions. We need to identify where the oxidation's occurring, i.e. where the electrons are being lost, where the reduction is happening, where the electrons are being gained. Then we need to make sure the electrons lost equals the electrons gained. In a similar way to in a acid-base reaction, we needed to make sure that the hydrogen ions being lost was the same as the hydrogen ions or the protons being gained. And then we basically put those two, the oxidation and the reduction, half equations, hence why we call them half equations, because they go together, to give us the whole balanced equation. So we'll go through what that looks like now. So the first step that we would do is identify the redox pair. That's usually given to you in the question, so you don't need to remember these. They're given to you in the question. I'm going to pick a particularly hard one, but one that we use a little bit. Dichromate going to form chromium ions. So that's our redox pair. Then in the first step, when we start doing this, we need to balance out any metal or non-metal atoms except oxygen and hydrogen. So just as it says there. So what does that look like? We've identified our redox pair, the dichromate ion going to form chromium ions. Just out of interest, the dichromate is orange, the chromium ions are green. So when this reaction happens, we get a really distinctive colour change from orange to green. So what's the bit that we need to add here? Well, we need to add a 2, so I'll do the new bits in red, a 2 in front of the chromium, so that there's now 2 chromium there, 2 chromium there, they're balanced. Then we go to step 3, where we're going to balance out the oxygen using water molecules. So if I just write down in green what I had on the left line before, Cr2O7 2- goes to 2Cr3+, and if you like the new bit, we need to balance out the oxygen. We've got 7 here, so we need 7 on this side, so that we need to then add 7H2O. Now we have 7 oxygens on this side, 7 oxygens on this side. Then we go to the next line. We're going to balance out the hydrogen using hydrogen ions, and that's where the acidic conditions come in to provide the hydrogen ions. So now we have the dichromate going to form the 2 chromium ions plus 7H2O, and you can see here we've got 14 hydrogens on this side, none on this side. So to balance out the hydrogen, we need to have 14H plus there. So now the hydrogen balance. And then in the final step, we need to balance out the charge using electrons. So if we just repeat everything we had written down here before. I'll show you the shorthand way to do these in a sec, so you don't have to write so much stuff down, but it's good to see it done step by step. And as I said, this is as hard an example as you'll need to do. So total charge on this side is 14 pluses and a 2 minus, so there's 12 plus here in total. Over here there's 2 3 pluses, so 6 plus. It's 12 plus, 6 plus, we've got to get them equal, which means we've got to make the 12 plus come down to 6 plus. We can't make there's no way to make 6 plus equal to 12 plus using negative electrons. So that basically means we need to have 6 electrons there. So the dichromate, basically the dichromate plus 14H plus 6 electrons goes to the 2 chromium ions plus water. So this is, again, the electrons are on the reactant side. They're on the left-hand side, so we must be gaining electrons. So this is a reduction process. So then this would need to go with something else that's oxidation. So basically, because this is being reduced, it'll cause the other thing to be oxidised. And then I'm not going to do this last step now. I'll show you this when I do the 2 examples in a minute. But we need to combine an oxidation half equation with this reduction half equation such that the electrons lost equals the electrons gained. I'll go through that in a sec. So, there's, I guess, the first 5 steps of the half equation method, and step 6 is turning them into a full equation. Let's have a go at doing a couple of simple examples here. So, let's look at this. Zinc metal reacts with copper 2 ions to form zinc 2 ions and copper metal. So I demonstrated this one in the lab last week when we dropped some zinc into some copper sulfate. So let's identify the 2 redox couple, the redox pairs. So the redox pairs are the zinc going to form zinc 2 plus ions, and the copper sulfate, so the copper 2 plus ions going to form copper metal. Now, going through the steps up here, identify the redox pair we've done from the question. Balance metal, non-metal, except oxygen and hydrogen. Well, zinc is balanced, copper's balanced. Balance oxygen, there's no oxygen. Balance hydrogen, there's no hydrogen. Balance charge using the electrons. So to achieve that, we need no charge, 2 plus here. So if we have 2 electrons here, the charge is balanced. Now see here, electrons are a product, so electrons, if you like, are being released. So this process here would be the oxidation, just put oxidation for short, and then at the bottom here, it's a similar process. Don't have another metal or non-metal, don't have oxygen, don't have hydrogen. So we would need 2 electrons here. Electrons are being gained, so this one here would be reduction because it's a gain in electrons. We talked about that before. Now, when we do the combined equation, we basically add these 2 together. We can simply add the 2 together because the number of electrons that are lost here is equal to the number of electrons that are gained. If that wasn't the case, then we'd have to basically use a multiplier on one of these equations. I'll explain that when I do the next example. So when we add everything up that's there, we basically add up all of the reactant side. We get zinc plus copper 2 plus. I will put the electrons in, we'll show they cancel out, plus 2 electrons. That adds up everything that's on the reactant left-hand side here, goes to everything that's on the product side, zinc 2 plus 2 electrons plus copper. Now you can see it's a bit like in mass. The plus 2 electrons is on that side and that side, so that effectively cancels out each other, and that simplifies to be Zn plus Cu2 plus goes to Zn2 plus copper. So that is, it's only an ionic equation. I haven't put the counter ions in, if you remember doing ionic equations where we ignore the spectator ions from earlier in the year, but that's all we normally need to do for these. and we've turned that into a complete electrochemical equation, or a complete redox reaction. If you like, we've done the step 6. Let's now look at the example here that I've given. Ethanol, CH3CH2OH, is oxidised by dichromate ions, which I talked about before, to produce ethanoic acid, also known as acetic acid, which is in vinegar, and chromium ions. So this is the reaction that the old breathalyzers used to use to see if you had ethanol or alcohol on your breath. Now, the dichromate ions are orange, sort of looks orange, I hope, and the chromium ions are green. So basically, if you've got alcohol in your breath and you blow it over some dichromate solution or crystals, you'll see a colour change from orange to green, indicating alcohol on your breath. It's the basis of how breathalyzers used to work. We will demonstrate this next year in chemistry, this reaction, when we do oxidation of alcohols. So, how do we write a redox reaction for this equation? And this is just about as hard as you could get. So, by doing a hard one, I'm hoping that the others seem simple. So let's firstly break it into the two half equations. And let's start off with the ethanol one. Oops, that's the highlighter, not the pen. So we have CH3CH2OH going to CH3COOH. So, done the first step, we've identified the redox couple from the question. Then we're going to balance out non-metal metal atoms other than oxygen and hydrogen. So we have 1, 2 carbon here, 1, 2 carbon there. So they're all good. Then we're going to balance our oxygen using water. We've got 1 oxygen here, 2 oxygen here. So we need to just add 1 water there. So that's balanced out the oxygen. Then we need to balance out the hydrogen. We have 3 plus 2 plus 1 is 6 plus 2, 8 hydrogen on this side. 3 plus 1, 4 on that side. So we need to balance 4, add 4 hydrogens here. So see how I'm doing this just all on the one line, not writing it out 5 times like I did above. And you can quickly get used to doing this all on the same line. And then finally I need to balance out the charge. So no charge here on the left-hand side. On the right-hand side we have a +4 charge. So we have to reduce that with 4 electrons, like such. So that is the half equation for ethanol being oxidised to form acetic acid. How do I know it's oxidation? Well, we have the electrons over this side as the product, so they're being lost. Therefore, that's oxidation. Now, let's look at what happens with the dichromate. Well, we've really just done that above, but I'll quickly do that again. I just want to change colour, sorry. That's not the colour I want. Yeah, we'll go with red. So we've got, that's not, get my highlighter mixed up with my pen all the time, sorry. So we've got the dichromate going to the chromium ions. We balance out the non-metal or metals other than oxygen and hydrogen, which is chromium, so we need 2 there. Then we need to balance out the water, balance out the oxygens with water. So we do that there, 7 waters, and then we need 14H plus. 12 plus on this side, on the left-hand side, 6 plus on the right, so we need 6 electrons there to balance that. So, we've got our two half equations now. the number of electrons lost must equal, down here, the electrons gained. This gets a bit tricky because we want 4 and 6. How do we make those equal? We're going to need to find the lowest common multiple of 4 and 6, which is 12. So 4 and 6 are both a factor of 12. What do we do from there? Well, that means that we need to have 12 electrons being lost. So we need 3 of everything in brackets there at the top. And then we need 2 of everything there, because that will now mean that 3 times 4, 12 electrons are lost. 2 times 6, 12 electrons are gained. So we're going to add them all together to get our combined equation. So add up everything on the left and then everything on the right. So we're going to have 3CH3 CH2OH plus 3H2O, because everything in that brackets has got to get times by 3, plus 2 dichromate plus 28H plus 12 electrons. So that's covered all of the reactant side. Now we're going to do the product side. Now I don't normally like splitting equations over 2 lines, but in this case I'm going to have to. 3 ethanoic acids, CH3COOH, plus 12H plus 12 electrons, plus 4 chromium ions, plus 14 H2O. Now we can simplify this a little bit, because we got 3 H2Os on this side here and 14 here. So basically we can get rid of all 3 of those and turn that 14 into 11. So basically we're taking away 3 waters from each side. We have got 28H plus here and 12 here, so we can get rid of that 12 and take 12 from 28, which means it's 16H plus. We've got 12 electrons on this side and 12 electrons on this side, and we know they should cancel out because the number of electrons lost must equal the electrons gained. And I think that's as far as I can simplify it. So that leaves us finally with 3CH3CH2OH plus 2 dichromate plus 16H plus goes to 3 ethanoic acid plus 4 chromium ions plus 11 H2O. Now, yeah, that's pretty messy and complicated. That's as hard as it gets. I could not have thought of a harder example. So this is about as easy as it gets. This is about as hard as it gets. Most of the ones that you're likely to need to do are somewhere in between that. So if you understand everything that's going on here, you will be able to do this for any reaction. That's it for the first Redox Reactions video on the whatever it was called, the concepts of oxidation and reduction. Wasn't exactly that, but I forget what it was, but hopefully you know what I mean. Thank you.